All right, so our next lecture series is going to cover free energy and thermodynamics. All right, so the main goals of this series is that we're first going to talk about the importance. Why is it important to learn about this? We're going to talk a little brief review of the first law of thermodynamics before we get into the second law of thermodynamics, which deals with something that's called entropy. So what is entropy? And then we're going to develop further into something called Gibbs free energy. All right, and then finally there is a relationship between this delta G naught, which is a standard state of Gibbs free energy, or the change in Gibbs free energy, and its relationship with an equilibrium constant for a reaction that is at equilibrium. You can use that to predict spontaneity, which is what Gibbs free energy does. Okay, so thus far we've been talking about this semester on macroscopic scale processes like kinetics, speeds of reactions. For equilibrium reactions, we can look at the K value and see what side of the equilibrium they lie to based on that K number, how far they're going to go to make products and things like that. We've looked at acid-base reactions, neutralization reactions, and expanded that farther into buffer systems. Okay, and then at the beginning of the semester, we also looked at various gas phase reactions. We know that gases expand to fill their containers. All right, so those are all some examples of chemical changes, but we also have physical changes as well. We have, just going from a solid to a liquid to a gas, or vice versa, which are, physical changes. And so a question comes about, why do these chemical reactions, or why do these physical changes even occur in the first place? Like, why do they happen? Okay, what is ultimately the driving force in a chemical reaction? What is the driving force in a physical reaction? So, if you have your gasoline in your gas tank in your car and you apply a little bit of heat, okay, you have a spark from your spark plug and there's some heat in there, it will spontaneously combust to make carbon dioxide and water, and obviously a couple other side products and things like that that come out through the exhaust. But why doesn't the exhaust turn back into gasoline, right? If I have some ice on, on my hand, and my hand is obviously warmer than the ice, why does the ice spontaneously melt into liquid? Why can't I take liquid water in a glass and spontaneously have it make ice, okay? At room temperature, why can't I do that? And so there is this driving force that is causing the chemical reaction to occur, or the physical change to occur, okay? And that driving force behind the chemical and physical change in the universe is a chemical quantity called entropy, okay? And entropy just means the dispersion or the spreading out of energy, or, going to chaos. And things like that. Okay, so that's just kind of an introduction into entropy, and we're going to take a look at how that explains why chemical and physical processes occur under a certain set of conditions. Okay, so we're going to talk a little about just a review on the first law of thermodynamics. Okay, so thermodynamics is concerned with energy changes that accompany chemical and physical processes. So usually when we see energy changes, we think delta, so state functions and things like that. And remember, whenever we're dealing with energy, we always have to identify what is the system and what is the surroundings. Okay, so the system is the thing that we are interested in, usually the chemical reaction itself, or the physical process, or the that's occurring. Okay, and the surroundings is everything else. Okay, so remember on thermochemistry, when we were trying to quantify the amount of heat that was released or required for a chemical reaction by measuring the temperature, Q equals mc delta T, right? We had to designate what our system was and what our surroundings was, and we were measuring the temperature change in the surroundings, and then back calculating and taking the inverse sign of that to get the heat of the system, which was our reaction. Okay, so first thing you always need to remember is when we're looking at these energy type problems, we always have to identify what's the system and what's the surroundings to solve them correctly. Okay, so just a reminder, first law of thermodynamics, all right, that states that energy cannot be created or destroyed. And that can be more commonly described by this equation right here, internal energy, U, okay, is equal to work plus heat, okay? And using the symbol notation here, not just U, but it's delta U, or the change in internal energy, is equal to work W plus Q heat. All right, so remember that this delta over here is a state function, and that means that internal energy itself only depends upon the initial and the final states of the system, okay? However, if you look and you see that work and heat, they are not state functions because they do depend on their initial and final states, right? So if we have a system and we add, if work is done on the system, okay, then that means that this term would be negative and the internal energy would be decreasing. Okay, if the system does work, then we would denote that as a positive, and then the internal energy would be increasing. If the system is, using a force and pushing something across a distance, that is applied work, that's positive. Okay, the same thing we can apply in terms of heat. For example, if you have a chemical reaction and heat is lost by the system, the chemical reaction, then we would denote this term as negative, and then the internal energy of that chemical reaction would be decreasing. Or if we had to apply heat or add heat to the system or to the chemical reaction, then that would be an endothermic reaction, right? And we'd have to add that heat that would increase the internal energy of that chemical reaction. Okay, so one of the main limitations of the first law of thermodynamics, which is why we need the second law, is that it doesn't tell us anything about the direction of a spontaneous change. Okay, so if I have an ice cube that's in my hand, okay, and it melts, right? The first law tells us energy was transferred from my hand to the ice cube to melt it, right, into a liquid. But why doesn't the ice transfer the energy back to your hand and then turn into, why doesn't the liquid transfer energy back into your hand and then turn into an ice cube, right? That's not violating the first law of thermodynamics, right? It's still a transfer of energy. Energy is not being created or destroyed. Either the hand is transferring energy to the ice and melting it, or the liquid water can transfer energy back to the hand and then the liquid water turns back into ice, right? Neither of those is violating the first law of thermodynamics. However, in the first law of thermodynamics is not telling us which direction or why the direction of it going from ice to liquid is the spontaneous change. The first law does not tell us that, okay? So the second law does. The second law does help explain why the ice will melt in our hand under certain conditions. Okay, so talk about a brief review of the first law of thermodynamics. So thermodynamics is concerned with energy changes, right? Energy changes that accompany chemical or physical processes. All right, and so remember back in thermochemistry when we were using Q equals mc delta T to calculate the heat of a chemical reaction that was either endothermic or exothermic. We always had to identify the system and the surroundings. So the system is usually our chemical reaction or our processes that we are specifically looking at, and the surroundings is everything else. Okay, so we always have to identify those when we're looking at energy type problems. Okay, so the first law of thermodynamics, right? Remember that is energy cannot be created or destroyed. Okay, and it's more commonly written as a chemical, as a mathematical equation. Internal energy U is equal to work W plus heat Q. Okay, and not only that, it's the change in internal energy, this delta U, and that delta means it's a state function. So we only care about the initial and the final states of the system. What we can see here is that work and Q are not state functions. They do depend on their initial and final states. All right, so we have the work of a system and work is being done by the system, then that would be a negative work and the internal energy would be decreasing. Or if the system, if work is done on the system, then that would be positive and the internal energy would increase. Okay. Same thing, we could look at heat if we're looking at a chemical reaction, and if heat is lost from the system, that would be exothermic and negative. The internal energy would be decreasing overall. And if it would be an endothermic reaction, we'd be adding heat to the system, then that would be positive, and the internal energy would be increasing on that. Okay, so one of the main limitations of the first law of thermodynamics is that it doesn't tell us anything about the direction of a spontaneous change. Right, so for example, when we take a look back at when I put the ice cube in my hand, right, the heat from my hand transfers energy to the ice, okay, to melt it, okay? But why doesn't it go the other direction? So that spontaneously occurs. If you put an ice cube in your hand, it will spontaneously melt because the heat from my hand is transferring energy to the ice and melting it into liquid. But why doesn't it go from liquid water and that liquid water transfer energy back to my hand and then the liquid water turns back into ice? That's not violating the first law of thermodynamics. Energy is not being created or destroyed. It's being transferred, okay, through a process of heat. But the first law doesn't tell me why the first example where the ice is being melted by my hand is the spontaneous way. It doesn't tell me why that's the spontaneous direction. It could go the opposite direction and still not be violating the first law, but it doesn't help me predict or explain that spontaneity. Okay, and the second law does. The second law helps to explain why that's so. So we can use the second law or this thing called entropy as a way to predict spontaneity for various processes and chemical reactions. Okay, so what is entropy? What is the second law of thermodynamics and how can we use it to help us predict the spontaneity of a process? Okay, so the second law of thermodynamics is everything basically goes to increasing disorder. Everything goes to chaos. Everything is always increasing in entropy, okay? So remember, entropy is dispersion, chaos, disorder of energy, okay? And so entropy is always increasing. And so if we're looking at a spontaneous process, any spontaneous process, the entropy of the universe is going to be increasing. Okay, so let's first identify and define what is a spontaneous process. Well, it's pretty much everything that you think it would be. It's a physical or chemical change that occurs by itself. It just spontaneously occurs by itself. And that it will continue without a continuous input of energy from outside of the system. Okay, so some things might need like a little spark or something to ignite it, but then they will continuously occur once they get going. Okay, one thing about spontaneous and the word spontaneous does not mean instantaneous. Spontaneous has nothing to do with the speed at which something is going to occur. Okay, so it doesn't mean it's fast, it's occurring fast. Has nothing to do with the time, right? So for example, ripening of fruit, aging, formation of diamonds, the rusting process, all of these are very, very slow processes. However, they are spontaneous. Okay, so don't get confused with spontaneous meaning it has to be fast, because it does not. We can still have spontaneous processes that occur at very slow rates. Okay, so this diagram over here is kind of a distinction between the difference between thermodynamics and kinetics, speed, something that's spontaneous versus something based on speed. Okay, so if we have our energy reaction diagram here, this is the energy of the reactants here, right? And the energy of the products here, the final. So we have the final state minus the initial state. That's just the change in energy. That's looking at thermodynamics. Okay, we only care about these state functions, the initial and the final states. Whereas the kinetics is what's occurring as we convert reactants to products, right? You have some mechanism occurring in here. We look at the activation energy, and the higher the energy, the slower the rate, the lower the energy, what a catalyst does, the faster the rate. Okay, and so that has to do with speed. Okay, thermodynamics has to do with initial and final energies. Okay, so a spontaneous process that is a physical change, can just consider the example. You have a ball and you give it a little push and boop, it's going to spontaneously roll down the hill. But it will not spontaneously go back up the hill. Even if you give it a little nudge, you know, with your foot to go back up the hill, it won't do that like it did very spontaneously and easily to go down, rolling down the hill. Okay? So chemical spontaneous change would be, we take a look at the alkali metals in column 1 on the periodic table. Their reactivity, as you go down the periodic table, they increase in reactivity. So we watched a video, I think last semester, where you take some solid of each of those metals and you throw it in some water and they become more violently and explosive as they react. So here we just have some potassium solid, you throw it in a little bit of water and boom, spontaneously it will kind of erupt, okay, and form this hydrogen gas, and a lot of times you can see the fire and things like that, the heat that's released from that. Spontaneous in the forward direction. And for a chemical reaction, if you go in the reverse direction, it would be non-spontaneous. So if you calculate that it would be spontaneous in the forward, then if you were to write the reaction in the reverse direction, that would be a non-spontaneous process. Okay, so I kind of alluded a little bit already to the fact that the second law of thermodynamics and entropy and things like that we can use to predict spontaneity. However, you can only determine if a process is spontaneously by calculating something called the Gibbs free energy. So that's delta G, okay? So you can only determine spontaneity by calculating Gibbs free energy. We can't specifically and strictly look at just entropy. We can say, oh, entropy is increasing or entropy is decreasing for a specific process, but we can't say that it's spontaneous just by looking at entropy, okay? If we want to know if it's spontaneous, we have to calculate delta G, and delta G is equal to enthalpy minus temperature times entropy, okay? And we'll talk about a lot more what this means here very shortly, okay? But anyway, the Gibbs free energy, if we calculate that and it is negative, then that means that it is a spontaneous process, okay? All right, so if I know some information about a process, if I know its enthalpy, okay, usually in red right here, okay, if I know a process is exothermic, so exothermic is negative release of heat, right? Negative and negative delta G, oh, that might be spontaneous, right? But we do have this term over here, minus T delta S, okay? This is usually small, okay, so it's not going to affect the number or value that the enthalpy is. Usually, okay, it can, and we do have to consider temperature, but usually if a reaction is, or a process is exothermic, okay, it's negative, then this is negative, and this is negative, and negative means spontaneous, then the process will be spontaneous, okay? Usually, if a reaction is endothermic, this is positive, positive, so positive and positive, it's non-spontaneous, right? Non-spontaneous, usually, okay? But there are some situations and scenarios where, depending on the temperature and what's happening with the entropy of the process, can kind of change that value for what we would usually think would happen, and it would be the reverse, okay? So we must also consider temperature, okay, when we do calculations, but usually we can predict spontaneity based on if we know the enthalpy of a process. If it's exothermic, okay, it probably is spontaneous. If it's endothermic and I have to put energy into it for it to occur, then that's not spontaneous. I have to put energy into it for it to go, okay, right? So it's not spontaneous, so it would be a positive delta G there, okay? Usually, not always, but that's kind of like a short way to kind of think, oh, maybe this is spontaneous or not spontaneous based on the enthalpy value here. Okay, so now we're going to talk a little bit more about entropy. So again, entropy is denoted as capital S, and this is a quantity that measures randomness, disorder, chaos, dispersion, any of those words in a system, okay? And it's a state function that we saw in that Gibbs free energy equation. So it also is delta S, and it depends on the initial and the final states of things in the system. Okay, this value, it only depends on temperature and pressure. So those are the two variables that can affect the entropy value. And it is measured in joules per Kelvin. Okay, and if we think back again to that Gibbs free energy equation. It was temperature times delta S. So we multiply by the temperature in Kelvin, and that would cancel out our Kelvin units there to give us joules. Okay. Another thing is this is in joules, and usually our enthalpies are in kilojoules. So when you add or subtract those numbers together in the Gibbs equation, you need to convert either this to kilojoules or your enthalpy to joules. Okay, so what does this entropy mean? Okay, the more disorder, the more randomness, the more chaos there is, then the higher the entropy number, the entropy value. Okay, and this entropy value, we look that up in a table. So these have been measured. They're in an appendix table, or you can look them up in a table online. Okay, so everything has some type of entropy value given. Okay, so it can never be less than 0. Okay, and that kind of gets into the third law of thermodynamics. Okay, so the S values are always positive. 0 is considered positive, so it's either 0 or greater that something is always designated as for its entropy value, okay? However, the change in entropies between a final and initial state, they can be negative, right? So if you are decreasing in entropy, then you have a smaller number minus a larger number, and therefore you would get a negative change in entropy, okay? Okay. So let's take a look at this example here to see, make it apply to what it really means. Okay, so here we have some ice. Okay, so we have water solid, and it's doing a phase change, and we are melting it into liquid water. Okay, all right. So if we think in terms of the structure of solid water, solid ice. Okay. It's very highly ordered. It's all crystallized structure, so it's very highly ordered. Liquid water is more movable. There's more space in between the molecules. There's more, it's a less ordered structure, okay? So the solid structure of ice, they're in a fixed position. They can't move very much. And the water molecules, they can freely move and pass by each other, okay? So the solid ice, the water, okay, solid water, has a low entropy. There is less randomness. There's less disorder. It's very ordered. It's very ordered. So it means it doesn't have very much entropy at all. Okay. Whereas the liquid water has more of this random motion. It's more fluid. So it has a higher entropy. It has more disorder. It has more randomness. Okay. So if I look these values up in an appendix table, I can get that this initial state for this physical process is at 41 joules per Kelvin, and the entropy of the final for this process is 63 joules per Kelvin. Okay, so if I want to calculate the change in entropy for this process, it's just final minus initial, so 63 minus 41 gives me a positive 22 joules per Kelvin. Okay, let's talk for a minute about this, this sign here. Okay, this is positive. So a positive change means that the entropy for this process, from the ice solid going to water liquid, increased. We increased in entropy, and we know that because this is more disorder than that. This is more entropy than that. Okay? So a positive change in delta S, a positive delta S, means that the entropy for that process, for that chemical reaction, whatever it is, increased. Okay? And spontaneity would be favored. It doesn't necessarily say that it is spontaneous, but it would definitely be favored because it also depends on the temperature and things like that and other conditions at which it's occurring. Okay, so spontaneity is favored if delta S is increasing. Okay, likewise, if I were to go in the reverse direction, I would be taking liquid water, right, and freezing it. Okay, if this direction is spontaneous, this direction will be non-spontaneous because now I would have a final minus initial. A smaller number minus a larger number would give me a negative entropy change. Okay, so a negative entropy change means that the entropy has decreased, and that's against the second law of thermodynamics because everything wants to go to increase entropy, okay, because they became more ordered, okay, then non-spontaneity is favored. Okay, so we can kind of look at the entropy values as a way to kind of predict whether or not the process will be spontaneous or not, but we really have to only calculate delta G for that confirmation for sure. But we can look at that as an indicator to say, okay, it's increasing, it should be more spontaneous for that process to occur, or it's decreasing entropy, it's going against disorders, becoming more highly ordered, it's non-spontaneously favored. Okay, so we're going to take a look at some generalizations about entropy for some reactions or processes, and we can use these generalizations in order to predict if entropy is increasing or decreasing just by kind of looking at the reaction equation, or the process that's occurring. Okay, the first one is an example that we've already taken a look at in the previous example, which was in changes in phase in the state. Okay. And so if we're going from a solid, which is really highly ordered, to a liquid and then to a gas, which is not ordered at all, it's very disordered, lots of entropy, then the highly ordered solid is low entropy because it has high order, not very much disorder, and going to a gas, which is very disordered and lots of entropy. So we can kind of just look at phases to see if entropy is increasing or decreasing without even having to look up the values of them in an appendix table to do a calculation. Okay, so we look at which phase is more or less highly ordered. Okay, is it really ordered or is it not very ordered? Okay, and if it is highly ordered, like a solid, that's going to have a low entropy value number that we would look up in a table. If it is less ordered, that means it's pretty random. We have lots of disorder and we have lots of chaos and dispersion. Then it's going to have a lot of entropy. And so then it's going to have a high entropy value that we would assume we would find in an appendix table. Okay, so if we take a look at this, is just carbon dioxide gas goes to carbon dioxide solid. So if I just look at the phases, it's the same substance but different phases. If I look at the phases, I can say this is a gas. It's lots of spreading out. Gases are spreading out, lots of disorder. It should have a high entropy number. And a solid should have a low entropy number because it's very highly ordered. It's against entropy. Okay, so we are decreasing in entropy. A small number minus a larger number should give us a negative entropy without even having to do the calculation. Okay. So this would favor non-spontaneous type of process. You'd have to have certain conditions in order to get that to go. Okay. The second generalization is as the number of particles in the system increase, then the amount of disorder increases. So you have more things being made on a product side, or then they're going to be colliding and moving around. Okay, so we would assume that the entropy in the system would be increasing if that is occurring. Okay, so here's an example. We have one molecule of the C4H8 in the gas, and we have two molecules of the C2H4 in the gas. So we don't need to consider phases, and usually you will never have an example where it will be combining multiple of these generalizations, because then it's too hard to predict and figure out what's occurring without doing a calculation. Okay, so here the phases are staying the same, so we're not looking at that, but what we can see is that, oh, we're making two molecules on a product side versus only one on the reactant side, and so I'm going to have more disorder on the product side, I would assume. Okay, and you actually can look up these values, and I can show you that, it's 219 for the entropy, and this one was 310 for the reactant, so it didn't increase in entropy. But the joules per Kelvin is per 1 mole. That is the value in the back in the appendix table. And we have two moles here, 2 molecules, 2 moles. And so we have to account for that. So if we actually do the calculation, it's going to be final minus initial. So we take 2 moles times the final entropy value minus 1 mole times the initial entropy value. And when I do that, I do get a positive 128 joules per Kelvin. So the entropy did increase. I have more molecules. I have more entropy there. So it does hold true. Okay, so you make sure you also account for the number of moles if you're doing the calculation. Okay? All right, the third generalization is as volume in which particles can move increases, then the entropy can increase, okay? And the reason for that is, the molecules can spread out more, and so the energy is dispersed more, and so there's more entropy that is created there, okay? All right, so here's an example. We have some air that's inside of a balloon, and I know how to spell balloon there. Okay? And the air in the balloon is going to be escaping out of a hole into a room. Okay? And so we're going to look at the air inside the balloon and the air outside the balloon. So initially, the air inside the balloon is in a smaller volume. Okay? So it's a smaller room to move around in. So the entropy is smaller. And the volume outside of the balloon is in whatever space it's going into, okay, has a more volume that it can move and disperse and spread out, okay? And so we would assume that there would be a larger entropy outside of the balloon that air molecules can move around in. So again, the air molecules outside of the balloon, they can spread out and they can disperse, and that is allowing the energy to be dispersed, and so the entropy therefore increases. Okay, so we have a change in entropy. A larger entropy minus initial will give us a positive. Okay, and then the fourth generalization is temperature. So as temperature increases, then that causes the kinetic energy of the particles to also be moving around much more frequently and randomly, and therefore entropy increases because there's more movement and randomness and disorder occurring, and we would have a change in entropy that would be positive, that would be occurring if we went from a lower temperature for a system to a higher temperature for a system. It would be increasing in entropy there.